Hi, my name is John Robert. I'm continuing on my series Fine-tuning LLM on your custom data. The first video, I explained the best data format required to fine-tune LLMs. Now we're going a bit further. In this video, I will explain why we need adapters like LoRA and QLoRA for fine-tuning LLMs. To understand why we need adapters like LoRA and QLoRA, we first need to look at how LLMs or large language models are built. Large language models are just neural network trained on massive amounts of data. Inside these neural networks are weights. The weight values determine how this model predicts the next word or tokens. When we fine-tune an LLM, all we're basically doing is just modifying these weights. So these weights are floating point numbers, which are basically decimal numbers. Under the hood, these numbers are stored as binary, that is 1 or 0. These 1 or 0s are then represented as bits. So to get the size or the memory size of a model, all you need to do is to multiply the data type in bits by the number of weights or the number of parameters. You can see that LLaMA has 2 trillion parameters. The mid-size model has 400 billion parameters, and the small size has 109 billion parameters. In fact, that is why they are called large language models, because they have large numbers of parameters or weight. We can also check some other models. For instance, GPT-4 has about 1.76 trillion parameters. Gemini 1.0 has about 1.5 trillion parameters. So you can imagine if you want to do the calculator, a trillion multiplied by some numbers. Now let me explain what these data types are. So we have different data types. We have floating point 32, that means it has 32 bits, 16, it has 16 bits. So the first number is the sign, and the second is the exponent, and the third is the matrica. Most new models actually use the B float, where you have more exponent than you have in the normal floating point numbers. For instance, 1.25 can be represented as this. The sign is to say if it's positive or negative. So this is supposed to be a 32, but you can also represent it as a 16-bit or even an integer. Now that we understand what the data types in bits are, we understand the number of parameters or number of weights, we know that this will make the size of the memory required to train the model or pre-train the model. Then we can understand why we need LoRA. So what is LoRA? You can divide the word LoRA into two: low rank and adaptation. So the rank is the number of linearly independent rows or columns. And adaptation is just that we freeze all the parameters we get at the trained model, and then we create a new pre-trained or fine-tuned parameters, and then we add both of them together. That's all we do in fine-tuning. So to understand what linear independent means, all it means is that if you multiply the 4th row by 0, you can get the 5th row. That means this 5th row depends on this, and the same thing with this. This is same as this, same. So you can remove this, and you can see that the rank is 4. You don't need to know fully how this really works, but this is just a simple way to explain what the rank of a matrix is. Now this is an overview of everything. For full parameter fine-tuning, it means that you have a model that has this number of weights, then you want to modify this, so you fine-tune this, and then you add it. So the out of the fine-tuned weights will be the same size as the trained weights. So if you do this, so you can do this by this, and then you get the same thing, and then you put both of them together. But what LoRA does is that it reduces the rank. In this case, let's say the number of rows and number of columns. And now if you do A times B, you still get the same size of this, but then you are doing less computation. And that's why LoRa is good, because it reduces the amount of computation you need to do. And in reality, we don't need all the parameters to be fine-tuned. If you fine-tune a few parameters, you can still get good result. But obviously, as you know, when you do fine-tuning based on your custom data, you should understand that this new model that you get by fine-tuning will forget some other things that it could do before. And that's where the memory loss comes from this because training all the old weights, and they are changing actually the weight in the trained model. What is QLoRa? QLoRa is same as LoRa. The only thing is that now we just reduce the number of bits. Another thing about bits is that if you reduce the number of bits from 32 to 4, it may reduce a bit in the number of accuracy, but you save a lot in the cost of fine-tuning the model. And you can see here, to fine-tune, obviously there are different parameters that you need to think about when it comes to fine-tuning the model, but if fine-tuning the whole parameters, you can spend as much as $500,000. And that's why most of these big companies actually spend a lot on buying NVIDIA chips, because it helps them in fine-tuning this, in training the model first to get this, and also in fine-tuning. But if you don't have that much money to spend, you can also get similar result by just using things like LoRa or QLoRa. It will make things cheaper. I've explained how LoRa and QLoRA works in theory. Now let's do a bit of practical. So here you just need to install bitsandbytes. This helps us decide the data type when loading the data. You may need Hugging Face login if you want to load a model that requires login. For instance, LLaMA requires login, but I'm using TinyLlama, I don't require login. Then I set the loading data type to 8 bits. I load my model. Then I set the rank to 8. The number of parameters I have when the rank is 8 is 1.1 million from 1.1 billion parameters. If I change the rank to 16, the number of parameters also increase. To summarize everything I've said, QLoRa and LoRa are just used to reduce the number of trainable parameters. What they do is that they reduce the rank, and based on the reduction in the rank, they can reduce the number of trainable parameters. QLoRa is just a LoRa that is being quantized. That means that it changes the data type from high precision, for instance, float 32 to float 16 or to int 4. Thank you so much for listening.